So today we're going to discuss energy transfer mechanisms in thermal processes, the second law of thermodynamics and heat engines, reversible and irreversible processes, the Carnot engine, heat pumps and refrigerators, the second law of thermodynamics, entropy, and we will solve some examples. So energy transfer mechanisms in thermal processes. First, we will discuss conduction. So energy transfer by heat is also known as thermal conduction. At the atomic scale, the transfer mechanism is an exchange of the kinetic energy between more energetic and less energetic atoms or molecules. So let's say, for example, you put a metal rod near a flame. It will only take a short amount of time before the end near you, before the end near your hand becomes hot. So this is because before you insert one end of the rod in the flame, the atoms are naturally vibrating about their equilibrium positions at room temperature, and when you place it in the flame provides energy to the atoms, and they begin to vibrate with larger and larger amplitudes. And these atoms here, vibrating at larger amplitudes, will collide with neighboring atoms and transfer energy in the process. So in a metal, another large contribution also comes from free electrons, not only bound electrons vibrating about their equilibrium position, but also from free electrons, which can also transfer energy from one region to the next through collisions. And this is why metals are good thermal conductors. Other materials such as paper or fiberglass are poor thermal conductors, and so are gases, and this is due to large distances between molecules. So conduction takes place when there is a temperature difference between two parts of the material, resulting in a flow of energy from the hot to the cold region. So let's suppose we have a slab of thickness dx and cross-sectional area A. And if one face is hot at a temperature Th while the other is relatively colder at a temperature Tc, then the rate of energy transfer by heat in watts P equal to Q over delta T is proportional to the cross-sectional area and the temperature difference, and inversely proportional to the thickness of the slab. And so we have the rate of energy transfer by heat is equal to K A times the absolute value of dt over dx, where K is a proportionality constant known as the thermal conductivity of the material, and dt over dx is the temperature gradient. So the thermal conductivity of a certain material is the reason why if you put one bare foot on a tile floor and the other foot on a carpet, the tile floor will feel colder, even though both have the same temperature. And this is because the tile floor has a higher thermal conductivity, and therefore the rate of energy transfer by heat from your foot to the floor is faster than in the case for the carpet. So your skin is sensitive to this heat transfer rate, not the temperature of the object. Both have the same temperature, but your skin is sensitive to the heat transfer rate. So the larger the temperature difference between your foot and the floor, the faster the rate of energy transfer will be. So suppose we have a uniform rod of length L that is thermally insulated along all of its parts except at its ends, which are in contact with reservoirs at temperatures of Tc and Th. When a steady state of flow is reached, then the temperature at each point along the rod is constant in time. And therefore, the temperature gradient is the same everywhere along the rod, and we may write that dt over dx is equal to Th minus Tc over L. And therefore, the rate of heat transfer is equal to Ka Th minus Tc over L. So let's say we connect two rods of different materials and the same length in parallel and in series. You can show that the rate of heat transfer is larger when the rods are connected in parallel. So now we will discuss convection. So suppose you put your hand near a flame. So this will warm your hand because the air directly above the flame is heated. And because it is heated, it expands and will have a lesser density, and this will cause it to rise. And this will transfer energy to your hands as it flows by. Okay, so the transfer of energy through the movement of a fluid is known as convection. So the drawing show convection currents in a tea kettle and in a room heated by a radiator. So let's say here in the tea kettle, the lower layers of water are warmed first and as a result expands and rise to the top because of their lower density. Okay, and at the same time, the denser cooler water falls to the bottom so that it can be heated. You can also see the convection currents at the beach. So during the day, the sun adds almost the same amount of energy to both the beach and the water. But since the sand has a lower specific heat than water, it reaches a higher temperature. And as a result, the air above the beach reaches a higher temperature than the air above the water, and so this lower density hot air above the land moves upwards, okay, and is replaced by the colder air, and this results in a breeze from the ocean to the land during the day. Okay. At night, the opposite happens as the sand cools much more quickly than the water because of its low specific heat. This makes the air above the water hotter than the land, and therefore the breeze direction is reversed and it is from the land to the ocean. So we will now discuss another method of energy transfer related to the temperature change, and it is through electromagnetic radiation. So all objects radiate electromagnetic waves continuously. Okay. Uh, and we shall see in other videos that any accelerating electric charge emits electromagnetic radiation. And since the temperature of any object is due to the random motion of molecules, and since these molecules contain electric charges, so it follows that any object radiates electromagnetic waves due to the thermal motion of its molecules, and this is known as thermal radiation. Okay. So the rate at which an object radiates electromagnetic waves from its surface due to thermal radiation is given by Stephen's law. P is equal to sigma A E T to the power 4, where P is the power radiated by the surface in watts, and sigma is Stephen Boltzmann constant given by this value. A is the surface area of the object in meters square, and E is known as the emissivity, and T is the surface temperature of the object in kelvins. So the emissivity has a value between 0 and 1 depending on the properties of the surface and is equal to the surface absorptivity, which measures the fraction of the incoming radiation that is absorbed by the surface. Okay, so an object also continuously absorbs electromagnetic radiation from the environment. At the same time, it radiates electromagnetic radiation into the environment, okay? Otherwise, an object would lose all thermal energy and its temperature would reach absolute zero. So suppose an object is at a temperature T and the surrounding environment is at T naught, then the net rate of energy from the object as a result of radiation is given by this equation. So if the object is in equilibrium with its environment, it will radiate and absorb energy at the same rate, and its temperature will remain constant. Okay, so when you see an object in a constant temperature, it's radiating and absorbing energy from the environment at the same rate. Okay, but if an object is hotter than its environment, it will radiate more than it absorbs, and so it will cool down. So energy arrives to the Earth by electromagnetic radiation from the sun. Um, so let's first define the intensity, which is the rate of energy transfer per unit area. The rate of energy transfer per unit area at the top of the atmosphere from the sun is Is, known as the solar constant, and is equal to 1,370 watts per meter square. So some of this energy is reflected back and the other is absorbed by the atmosphere and then re-radiated by the Earth. Okay, so for Earth, only 70% of the incident radiation from the sun reaches the surface of the Earth. And so we may write that the power or rate of energy transferred into the Earth's surface, P input, is equal to 0.7 IS ISAC, okay? And AC is the circular cross-sectional area of the Earth given by pi radius of the Earth squared, okay? And the energy re-emitted as thermal radiation from the Earth's surface, and if we assume that the Earth is a perfect emitter of emissivity 1, then this energy that is re-emitted by radiation from the Earth's surface is given by this equation, okay? And so from this we can calculate the temperature of the Earth's surface by this equation, and using so A here is equal to 4 pi radius of the Earth squared, and this gives a temperature of 255 kelvins, and this is the average global temperature of the Earth's surface. But measurements show that the average temperature is warmer and is actually 288 Kelvin instead of 255 Kelvin. And this is because we did not account an additional effect from the atmosphere that can trap more energy and raise the temperature of the Earth. We will not go through details of that here, but you can find it in any textbook. So in nature, only certain types of energy conservation processes takes place that has a certain direction. And the direction of these energy conservation processes, it can be expressed using the second law of thermodynamics. So for example, energy transfer by heat is always from the warmer to the colder object. But nothing in the first law of thermodynamics tells us that heat cannot transfer in the opposite direction from the cold to the hot. But it is the second law of thermodynamics that determines the direction of such natural processes. So another example is if we have a container that contains two different gas molecules that are separated by a membrane. So if this membrane is punctured, the two different gas molecules will naturally mix together, and after they are completely mixed, we don't see them spontaneously self-organizing, where each different gas molecules go into one side of the membrane. So this goes to this, but we never see these molecules, the blue molecules, the green molecules, spontaneously self-organize into themselves into two different parts of the container. And another example is the free expansion of a gas, in which if we have a gas trapped in a vessel by a membrane and in which half of it is vacuum, and if the membrane is removed, the gas will expand to fill the whole of the vessel. But we will never see a gas suddenly spontaneously going back to fill only half of the vessel. So this direction, we have this direction, this direction, this direction. We do not see processes in the other direction, and the direction is given by the second law of thermodynamics. So these all are examples of irreversible processes that occur only in one direction. So the heat engine is one device that can only be understood using the second law of thermodynamics. It is a device that converts heat to work. Okay, experiments show that only a fraction of the input heat can be converted to useful mechanical energy, and that it is impossible to build a heat engine that converts all of the input energy to work. So we have heat coming in, some of it is converted to useful mechanical work, but we have remaining heat here, waste heat. Um, so we, we cannot convert all of the incoming heat into useful work. Okay. The figure shows a schematic representation of the heat engine. The working principle is that a substance absorbs heat from a high temperature energy reservoir. Some of this heat is converted to work, and work is done by the engine, and the remaining energy is expelled as heat to a cold reservoir. Okay. So the engine absorbs a quantity of heat QH from the hot reservoir. It does work, and then it gives energy QC to the cold reservoir, and this output energy is known as waste energy or exhaust energy. So as an example, let's consider the steam engine. The substance used is water, and this substance is carried in a cycle. So first, in a steam engine, water absorbs heat from a burning fuel like coal. It evaporates into steam and expands against a piston doing work. Okay, the steam is then condensed with cooling water and is returned to the boiler, and the cycle repeats. So the steam engine can be used for motion such as the steam train or to generate electricity, and this we will see in videos of electricity and magnetism. So going back to the general heat engine, because the working substance goes through a cycle, its initial and final internal energy is equal, and so the change in the internal energy of the working substance is equal to 0. And so delta E internal is equal to Q plus W, and we may write that Q net is equal to minus W and is equal to W engine, which is the work done by the engine, and this W is the negative work done on the engine. Okay. So the net heat is Q equal to absolute Q H minus the absolute value of QC, and it's equal to the work done by the engine. So if the working substance is gas, then the net work done by the engine for a cycle is equal to the area enclosed by the curve on the PV diagram as shown in the figure. And the thermal efficiency of a heat engine is defined by the work done by the engine divided by the input heat. Okay. Since QC is never equal to 0, which means there is always some energy that is expelled to the reservoir, it follows that E is never equal to 1, and the heat engine's efficiency is never 100%. So it's impossible to construct a heat engine in which all the input energy is converted to useful mechanical work. So all engines must exhaust some waste energy into the environment. And this is a statement of the second law known as Kelvin-Planck statement. We will now define reversible and irreversible processes. So, a process is reversible if the system can be returned to its initial state along the same path, and if every point along the path is an equilibrium state. And the process that does not meet this criteria is irreversible. So, all of the processes, the three processes we mentioned previously, are irreversible processes. And an example of a reversible process is if a piston is compressed very slowly in an isothermal process such that the pressure, volume, and temperature of the gas at each stage is well defined and the system is nearly in equilibrium at each point as it is compressed. And, and this process can be reversed if the applied force is gradually and slowly lessened so that the gas slowly expands back to its initial condition. We will now discuss a theoretical ideal heat engine that is the most efficient engine possible, and it is known as the Carnot engine, described by the French engineer Sadi Carnot, and it gives an upper efficiency limit for all real engines. And this means that the Carnot cycle gives the greatest amount of work possible for a given input energy. Okay? So to describe it, the working substance is assumed to be a gas in a cylinder with a moving piston, and the walls of the cylinder and the piston are thermally non-conducting or insulating. And the cycle consists of four processes, all of them reversible. So first, as you can see in the figure, the gas goes through an isothermal expansion at a constant temperature Th from state A to state B. And as it expands, it absorbs an amount of energy QH from the reservoir and does an amount of work on the piston W1. So as you can see, it's isothermal, so the cylinder is in contact with the heat reservoir. So as it expands, it will absorb an amount of energy of heat QH from the reservoir to maintain its temperature at TH, so that is isothermal expansion. And the work that the gas does on the piston is W1. And so when it reaches state B, the base is replaced by a thermally non-conducting material, and the gas then expands adiabatically from state B to C. And as it expands adiabatically, its temperature drops from TH to TC. Okay, and the gas does an amount of work W2 on the piston. So in an adiabatic process, Q is equal to 0. Okay, and when it reaches state C, the gas is put in thermal contact with an energy reservoir at temperature Tc, the temperature that it reached after the adiabatic expansion. So then the heat reservoir is at temperature Tc, and the gas will be compressed isothermally. And during the isothermal compression, okay, the gas will expel an amount of heat Qc to the reservoir to maintain its temperature at Tc, and the work done on the gas is W3. So here the work done on the gas is W3. And then when it reaches state D, the base is again replaced by thermally non-conducting material, and the gas is compressed again adiabatically from state D to A. So, and then as it is compressed adiabatically, the temperature of the gas will increase from Tc to Th, and the work done by the piston on the gas is W4. So adiabatic compression, Q is equal to 0. And this is the PV diagram for this cycle. So as you can see, from A to B, it's an isothermal expansion. Then we have an adiabatic expansion from B to C, then isothermal compression and the adiabatic compression. And Carnot showed that the absolute value of QC over QH is equal to TC over TH, and this gives the efficiency is equal to 1 minus TC over TH. And so Carnot showed that a heat engine operating in this ideal reversible cycle between two energy reservoirs is the most efficient engine possible. And this equation shows that the efficiency can be unity only if Tc is equal to 0 Kelvin, which is impossible since it is not possible to reach absolute zero. And therefore the efficiency is always less than 1. Okay, so all real engines are less efficient than the Carnot cycle because they are not carried out slowly enough for the processes to be reversible. So all real engines, when they operate, they are not operating in this reversible slow processes. So the efficiency is always less than Carnot cycle. So we will now discuss heat pumps and refrigerators. In a heat engine, the energy is transferred from the hot reservoir to the cold reservoir, which is the natural direction. As you can see, this is the natural direction from the hot reservoir to the cold reservoir, okay? But if we want the energy to transfer from the cold reservoir to the hot reservoir, we need to transfer some energy into the device, okay? So for that to happen, so since it is not the natural direction of flow. And such devices operating this way are known as heat pumps or refrigerators. And the schematic representation is shown here, where the cold reservoir is at Tc and the hot reservoir is at Th, and the heat absorbed by the heat pump is Qc, and the heat transferred out of the heat pump is Qh, and the heat transferred to the system is W. And although it is not necessary, may not necessarily be in the form of work, so since most heat pumps operate on electricity, but here we are keeping it in the form of work for convenience, okay? We will not discuss heat pumps here in detail. You can find it in any textbook, but just giving a rough idea about it. And a refrigerator is an example of a heat pump. So it cools its interiors by pumping energy from its inside to the warmer air outside. Okay, so heat is pumped from the inside to the outside. And in this process, the motor of the refrigerator does work on the coolant fluid. Okay. So the second law of thermodynamics can be expressed in different ways. We previously expressed it in terms of the efficiency of a heat engine. We will now define entropy and see how the second law is related to entropy. And entropy is a state function like internal energy. Okay, so and it's related to the second law of thermodynamics. So let's consider a system that is undergoing an infinitesimal reversible process from one state to another, okay? If dQr is the energy transferred by heat as the system follows a reversible path during that process, then the change in entropy, ds, regardless of the path taken between the two states, remember, because it's a state function, does not depend on the path, is then equal to the energy transferred by heat divided by the absolute temperature of the system, T. Okay? So as we said, the entropy is a state function. It means it's a function only of the initial and final state of the system, the same way internal energy is. And the change in entropy here is the same for all possible paths between the same initial and the same final states. So even though we defined entropy here in terms of a reversible process, even if the system follows an irreversible path between the same initial and final states, the change in entropy would be the same as the one in the reversible process if we have the same initial and final states. So if you have an irreversible process and you want to calculate the change in entropy, you need to define a reversible process between the same initial and final states and calculate the entropy. Okay. So the above equation here applies only for a reversible process. That is why we use the subscript R for dq, referring to a reversible process. As you can see here, if energy is absorbed by the system, then dqr is positive and the entropy will increase. And if energy is expelled by the system, dqr is negative and entropy will decrease. So for a finite arbitrary reversible process, delta S is equal to integration initial to final dqr over T. Okay. Also, for a reversible adiabatic process in which there is no heat transfer, the change in entropy is equal to 0. But take note here that this is true for only a reversible adiabatic process, not any adiabatic process, as we see in the following slides. So just for a reversible adiabatic process, delta S is 0. Also, you can show for a Carnot cycle, since d minus QC over TC is equal to QH over TH, sigma Q over T is equal to 0, which means that delta S is equal to 0. And also for any reversible cycle, entropy, since entropy is a state function, the change in entropy is 0. And in all these cases, whenever the change in entropy is 0, it is known as an isentropic process. We will now consider what is entropy. So entropy is a measure of disorder, and isolated systems tend towards disorder. Okay. So far, we have considered entropy from macroscopic concepts, but entropy can also be treated from a microscopic point of view through a statistical analysis of molecular motions. So we have talked about some irreversible processes previously that proceed in one direction. For example, we said that heat flows from the hotter to the colder object because initially molecules are sorted into a hotter and a colder region, which is an ordered state. But this order is lost when the system reaches thermal equilibrium, and the disorder of the system is increased, which means entropy is increased. Okay. Also, as another example, if we add heat to an object, the entropy or disorder will increase because the average molecular speeds will increase and the randomness of the molecular motion increases. And another example is the free expansion of a gas, where the molecules will have a greater randomness of position after the expansion instead of being sorted out and ordered at one side of the container. So this is the natural direction, is that the entropy will increase. So consider if we have a macro state. So each macro state has a number of microstates associated with it. And the more probable macrostates are the ones with a large number of microstates. So to understand this, let's first assume that all microstates are equally probable. And let's call the macrostates with many microstates in them the disordered macrostates, while the macrostates with few microstates in them the ordered macrostates. Okay. So as an example, suppose you have 4 identical arrows that can point either up or down, and you toss them randomly, but each of them may either land only in 2 directions, either up or down. Okay, so you toss these identical arrows randomly. So if you a macrostate with 4 arrows pointing up, this kind of state with 4 arrows pointing up has only one possible microstate, as you can see. And a macrostate with 3 arrows pointing up and 1 down has 4 possible microstates. You see 1, 2, 3, 4. So each microstate corresponds to the same macrostate, but you can see there are 4 possible microstates because the downward arrow can be in different positions. Okay. And there are 6 possible microstates for a macrostate in which half the arrows are pointing up and half down. So 1, 2, 3, 4, 5, 6 possible microstates for this macrostate. And there are 4 microstates for a macrostate in which 3 arrows are pointing down and only 1 is pointing up. So 4 possibilities here. And there is only 1 microstate for a macrostate in which all arrows are pointing down. And this shows that for a given macrostate, there can be many microstates corresponding to the same macrostate, right? So as you can see, the least possible macrostates here are the ordered macrostates, where either the arrows are either all up, or all down. So these ordered macrostates are the least possible. Okay, and this is the most probable because we have more possible microstates here. So imagine if we have an Avogadro's number of arrows. Imagine n is equal to Avogadro's number. Then the highest probable disordered state, such as this one, this is a disordered macrostate, can be well predicted. Okay, and you can imagine that the disordered macrostate will be way more probable than an ordered macrostate in which an Avogadro's number of arrows are all pointing up or down. Imagine an Avogadro's number of arrows all pointing up. Imagine this state. It is a highly ordered state and it's really highly improbable. And the disordered macrostate will be much or way more probable and it can be well predicted, right? So disordered states are more probable. Why? Why disordered states are more probable? It's simply because there are more microstates there. Okay? And so this is why an isolated system tends towards a more disordered state, which means towards a higher entropy. So let's see here a definition of entropy in terms of the number of microstates associated with a certain macrostate. So S is equal to KB ln W, where W is the number of microstates associated with a certain macrostate that has an entropy of S, okay? So the entropy statement of the second law of thermodynamics is that the entropy of the universe increases in all natural processes. Okay, so they tend to a disordered state. So let's consider isolated systems. So the total entropy of an isolated system may either increase if the process is irreversible or it remains constant if the process is reversible adiabatic process. Okay, so And take note here that the change in entropy is not zero for any adiabatic process. For example, the entropy increases for an adiabatic free expansion, but the change in entropy is zero only for a reversible adiabatic process. So the second law of thermodynamics can also be stated as the total entropy of an isolated system that undergoes a change cannot decrease. So it either increases for an irreversible process or it remains constant for a reversible adiabatic process. And in the case the system is not isolated, we must consider the change in entropy for the system and its environment. And for an irreversible process, the total entropy always increases because the increase of entropy in one part of the universe will be greater than the decrease in another part, and therefore the total change in entropy will be greater than zero for an irreversible process. Okay. So as an example, consider water freezing and forming a snowflake, which is a highly ordered state. So while it freezes, the water releases energy into the environment that will create disorder somewhere else. And this disorder will represent an increase in entropy that is larger than the decrease in entropy in the snowflake itself, okay? And the total entropy of the universe will increase as a result. This is why entropy always increases in an irreversible process. And ultimately, the universe may reach a state of maximum value of entropy, a state of perfect disorder where the whole universe is in a state of uniform temperature and density, and in which there is no energy available to do useful work. And this is referred to as the heat death of the universe, where all biological processes will cease. But of course, this is just a speculation and is not necessarily true. So let's consider now the example of the change in entropy in melting. So if a mass m of a substance melts at a temperature Tm, and if the latent heat of fusion is Lf, we want to find the change in entropy of the substance. And since melting takes place at a fixed temperature, the process can be regarded as isothermal and also can be reversed if the substance is placed in a cool environment so that heat leaves the substance instead of entering it. And so we have delta S is equal to integration of dqr over T, and this gives us LFM over Tm. Okay, so from a microscopic point of view, we can also see that entropy increases when a solid melts because the molecules in a liquid state are much more disordered than in a solid state. So let's now calculate the change in entropy in a free adiabatic expansion of an ideal gas. We know that this process is irreversible. And since the walls of the container are thermally insulating, no heat is transferred to the gas, and we have Q is equal to 0 and W also is equal to 0. And this means that delta E internal is equal to 0, and so the initial E internal initial is equal to internal final. And since in an ideal gas the internal energy depends only on temperature, then it follows that the initial temperature is equal to the final temperature. Okay. So to calculate delta S, we must find an equivalent reversible path from the same initial to the same final state as this one. And this can be an isothermal quasi-static reversible process. So this is the equivalent reversible path that we can substitute for this irreversible process to be able to calculate the change in entropy for this process. So remember, the change in entropy does not depend on the path because it's a state function like the internal energy. And so the change in entropy for this situation will be the same for that because they have the same initial and final state. And so we have delta S is equal to 1 over T integration of dQr, and T is, we put it out of the integral because it's constant in an isothermal process. Okay. For an isothermal process, we know that dQr is equal to minus dW, the work, and is equal to PdV. And from that, you can find that delta S is equal to nR ln V final over V initial. And since V final is greater than V initial, it follows that delta S is positive. Okay. So suppose for this previous example of free adiabatic expansion, suppose that the gas expands to four times its initial volume, okay? And we want to find delta S using this equation, which is the change in entropy from a microscopic point of view, and compare it to the change in entropy from a macroscopic point of view given by this equation. So using this equation, you can find that delta S is equal to nR ln 4 because the final volume is 4 times the initial volume. Okay, and we will not go to the details here, but you will find that in any textbook that the number of available microstates or locations for a single molecule in a gas that occupies an initial volume Vi is given by this equation, where Vm is the microscopic volume occupied by the molecule, by the single molecule, okay? So let's assume that each of these locations, so this is the number of possible microstates, and let's assume these microstates, each of them, are equally probable, okay? So the number of available states for n molecules, neglecting the small probability that two molecules will occupy the same location, is given by Wi is equal to Wi to the power n. And the number of available microstates for n molecules when the volume is V final is also given by this equation. And so the change in entropy, which is the same, this change in entropy, which is given by this equation, KB ln W final minus KB ln W initial, will give us this value, which is the same value obtained using the macroscopic definition of entropy. So we see delta S is equal to delta S using the two different equations. So thank you for watching, and please don't forget to press the like button and subscribe. And I included some two solved examples in the following slides. Hope you enjoyed the video, and see you in the next video.